Hi, good morning. Welcome everyone to this webinar. It's organized by CASTIEL 2 or Package 4, and we are very glad this morning to hear from NCC Italy. And NCC Italy represents one of their new services to share the information with our network of EuroCC2, CASTIEL 2, EuroCC4C. So today the webinar is organized with Simone Bna from Cineca, and Simone will introduce to you the speakers and chair this webinar for NCC Italy. And with this, Simone, the floor is yours.
Okay, thank you, Marie-Françoise. So welcome everybody to this webinar related to SPUMA, to the presentation of our GP reporting made here in Cineca. Just 2 words about myself. I'm the coordinator of the CFD group here in Cineca, the Italian Supercomputing Center. And I was one of the developer of the SPUMA software. So let's start with an introduction of EuroCC by Eric, our project manager here in Cineca. Please, Eric, left the word.
Thank you, Simona. EuroCC Italy is the Italian competence center of EuroCC network, and we are 5 partners: Cineca, IFAB, Birex, and 2 industry, Leonardo SPA, and Dompe Farmaceutici. EuroCC Italy have 3 main action through industry. The first is training. We have a very large training program for industry. The second is technology transfer in dedicated for implementation of new algorithm, train AI model, and we also develop some services like data lake or RAG system. And the third action is help the industry to find the the right open call to obtain computational or human resources to implement their POC. Today, we are happy to help the CFD team of Cineca presenting SPUMA. It's open source fork of OpenFOAM. We are very happy because it's a new implementation of GPU. I think the artificial intelligence is a very important topic today, but we don't forget the classical HPC implementation and technique. So EuroCC Italy try to help also the high people, but also the HPC people to implement a new solution on the cluster. Thank you.
Okay, so the next speaker is Tommaso Zanelli, which give you an introduction to Cineca and to the HPC systems here.
Well, good morning, everyone. My name is Tommaso Zanelli, and I will give you a brief introduction on who we are and how the work that we are presenting originated. Okay, so let's first talk a little bit about Cineca. Cineca is the largest provider of high-performance computing services in Italy. It is a consortium of Italian universities and public research institutions, and it is a major player in the European HPC landscape, participating in many of the Euro-HPC joint undertaking projects and initiatives, such as EuroCC or Hexaphone, which I will be talking about a bit later. And my colleagues and I are part of Cineca's POC team, which is dedicated to support of the more industrial applications of HPC. Eric curates more of the business development side of our activities, among other things, while Ettore, Giuseppe, Simone, and I specialize in CFD-related applications of HPC. We started working on OpenFOAM, on the code itself, in the context of the Hexafoam project. And basically, when we talk about OpenFOAM, we are talking about a code that was developed in especially the late 1990s, early 2000s, at a time in which massively parallel architectures based on large numbers of general purpose CPU cores were the norm in high performance computing, replacing the previous vector machines. And this context drove many of the choices that were made when developing the code, such as its message passing approach to parallelism or its sparse short-lived data structures. And what we see now is that modern HPC clusters are increasingly based on hybrid CPU-GPU architectures, with the latter providing most of the computational power in terms of floating point operations per second. And GPUs work differently. They implement a fine-grained approach to parallelism. They offer a large amount of memory, but with a higher cost per location, and they work best on highly coherent, compact data structures, which is not the case with codes like finite volume simulation codes, which instead, for example, OpenFOAM uses indirect addressing, which does not really marry this philosophy very well. So porting a code like OpenFOAM to GPU is a challenging task. Now, the Hexafoam project was a EU-funded project that ran from 2021 to 2024, if I recall correctly. And its aim was to improve the performances of OpenFOAM on modern HPC clusters. This, of course, covered many topics. The one that Cineca worked on the most was exploring whether it would be feasible to realize a GPU porting of OpenFOAM. Because at the beginning of the project, it was not at all clear whether this could be done effectively without having to do a significant refactoring of the code itself, of its algorithms and data structures. Cineca's main contribution was the development of a small demonstrator, which we called Zeptofoam, in which we recreated a small number of OpenFOAM solvers able to run fully on GPU. And basically, we realized that considerable performance gains could be gained without having to do this significant refactoring. So, leveraging on the experience that we gained from this demonstrator, we started working on full porting of the code to GPU, which is the work that we are presenting today. Now my colleague Ettore will give you an overview of the structure of this webinar and the scope of our work. Thank you.
Good morning, everyone. I hope you can hear me well. Let me quickly share my screen. Okay. Okay. First of all, thank you very much for joining this webinar. I'm very happy of seeing almost 100 people with such a short notice. It means that OpenFOAM and GPUs are an interesting topic today. I will try to present this webinar and also give you a very short introduction to SPUMA. This webinar has been organized for two main reasons. Of course, the first one is presenting SPUMA, which is our idea of a GPU porting of OpenFOAM. It means simulation processing on unified memory accelerators. We focused a lot in making this porting a non-invasive porting of OpenFOAM and to make it a portable and single source code base implementation. This was very important to us, and I think we managed to let's say correctly do it and simulating incompressible cases without altering too much the structure of the code. Most important, it allows other developers into completing and also introducing new features into SPUMA by starting from the OpenFOAM traditional implementation, even if they are not big experts of accelerators and GPU coding in general. This webinar is not only about SPUMA, but it's also about the ideas and the perspectives of some experts and researchers that are very known in the OpenFOAM environment to share their thoughts on the modernization of OpenFOAM and also the GPU execution. So I would like to thank them a lot for joining this webinar and presenting their work or their ideas, helping us in finding a common direction for reaching a GPU version of this software. The first speaker will be Gregor Olenik. He is leading let's say a development of a novel GPU-ready finite volume code, which will be also completed by OpenFOAM APIs. We think this is interesting because it might reach better performances than SPUMA in the future if the implementation is successful, and it's probably a more medium to long-term project, but we believe that it was good to have him here and to explain what they are doing in the latest months. The second speaker will be Charlie Mockett. We had the chance of collaborating with him during the development of our prototype Zeptophone. He supported us with a POC, and he was able of testing this Zeptophone prototype. And I think it's very interesting to hear his presentation because it will help us to understand the requirements of industrial end user with a specific look at the automotive CFD market. Then a very interesting implementation that was one of the outcomes of the Hexaphone project, which will be presented by Gregor Weiss, which is the coherent I/O in OpenFOAM. We think this feature is unlocking very large simulations because it reduces a lot the decomposition and reconstruction issues that OpenFOAM currently has. And also it unlocks hybrid workflows. If we think of end user that wants to simulate CFD on a hybrid cluster, moving from CPU to GPU partitions, well, if you don't have the bargain of the composition, it's definitely easier to run part of a simulation on GPU and the other part on CPU, post and pre-processing on different hardware. So it's very useful in my opinion. Then we will have Simone, and lastly Henrik Rusche from Wiki will talk about how an innovative CFD code should be designed. We were having this meeting with him and discussing the coherent I/O implementation, since also Wiki was involved, and we started having a discussion on OpenFOAM and finite volume, but also a CFD software in general, and we thought his vision was very interesting, so we decided to invite him and give a speech here, and he will be the last speaker. So this is the agenda. I will leave the floor to Simone to introduce the first speaker, and thank you very much again for your participation.
Okay, thanks, Ettore. So I think it's time to start the webinar with interesting discussions and presentations. So the next speaker is Gregor Omenik from TUIM. Is in the call.
Yes, normally.
Okay. Welcome. So, I think you can start. I need my microphone.
Okay, let me share my screen real quick. Oh, of course, yeah. Can you see my screen?
Yes, full screen, perfect.
Okay, and the audio is working, I guess.
Yes.
Yeah, I can hear you.
Okay, then first of all, thank you for the invitation and thank you for having me. I want to give a quick overview of what we are doing, but also to give a bit of a historical overview where OpenFOAM comes from and how the HPC landscape has changed over the time.
Sorry, Gregor, the participants is obscuring part of your presentation. Thank you.
All right, yeah, but first of all, let me say some quick words how this work actually started. So this work is part of the ExaSim project, which is a project funded by the German Ministry of Research, which is part of the ScaleExa project. And within the ScaleExa project or the ExaSim project, there are several partners. One is Upstream CFD, who is also here today, represented by Charles Mockett. And then there are two institutes at the KIT, so the Institute of Fluid Mechanics and the Scientific Computing Center. And the idea was basically to incorporate Ginkgo as a GPU backend for OpenFOAM. And what we did was we developed a plugin for OpenFOAM, which is very similar to Petsy for Foam. Our plugin was called OGL, which is the OpenFOAM Ginkgo layer. And it demonstrates that there's some benefit in offloading to GPU via a plugin in OpenFOAM. However, there's an inherent obstacle in the architecture of all plugin approaches. Basically, you only can offload the linear solver part and the matrix assembly part, which can have a substantial cost for the simulation is very hard to offload via a plugin. So either you have a case which spends most of the time in the linear solver, or you have to really find a way how to also address matrix assembly and bring that to the GPU. Because basically, if you run something on the GPU, you have to make sure that the communication between the host side and the GPU side is minimal. Otherwise, the performance gains are not substantial. So basically, we needed a way to also address matrix assembly. And this is where people, not only me, but people from other working on other projects contacted us and said, what you're doing is interesting, but can we also go to matrix assembly? And this is where the whole NeoFoam or Neon project started. But let me give a bit of a personal view of how I got involved in OpenFOAM. And I think it's a typical way how people start with OpenFOAM. So the first version I used was actually OpenFOAM 1.4. And it was back then the only, for me, available code that could handle fluid structure interaction and was open source. And that was during my studies. Then for my diploma thesis, I also used OpenFOAM to simulate droplet breakup. And then during my PhD, I worked with OpenFOAM because I did combustion, and OpenFOAM provided some combustion models, but also it was easy to some extent to implement like complex models. And I think this is a typical story how people get involved with OpenFOAM, because basically in OpenFOAM you will find anything from fluid structure interaction to chemical reaction models to advanced non-Newtonian fluids. And if there's something not in OpenFOAM, you can implement it yourself. So basically, every research institute who does anything with with fluid flows, they at least know OpenFOAM. And this is what I think is the main reason why OpenFOAM is a really interesting tool and has such a wide outreach. And yeah, because if there's any problem, OpenFOAM will have some tool for it. However, since OpenFOAM started, which I looked it up, the first initial release was in December 2004, I would say that the HPC landscape and also the software development landscape has changed quite drastically. And even though the first release of OpenFOAM was in 2004, the work on OpenFOAM is much longer. So, and I would argue the way how we as a community, the HPC community, develop software has changed a lot. So here's OpenFOAM. Right before OpenFOAM started, 3 years ago, there were, in 2001, CMake was released. LLVM started 2003. Git actually started after OpenFOAM was first released. CUDA was in 2007, and C++11 obviously in 2011. So these are all things which became mainstream after the first release of OpenFOAM. And I think that is something we really have to consider for the future development or the new development of any HPC code, that the tools have changed a lot. Since the whole project has started with GPUs in mind, we also have to look at like how GPUs became more or less mainstream. And here, 2018 was a really important year, because it was the first year when most flops added to the top 500 list were actually leveraged by GPUs. I also looked it up, like the first GPU accelerated machine in the top 500 was, I think, 2011-ish. Yeah, but nowadays, GPUs are not the future anymore, it's the present. So yeah, and then another really important catalyst for GPUs and HPC was the ECP project, which started 2016 and went on to 2024. So now, with all these changes in the HPC world and in mind, we really have to think about like what is the competition? What are the competitions to OpenFOAM? And first of all, I would also argue that, yeah, there are a lot of different GPU-focused projects in the OpenFOAM world, like OpenFOAM HMM, SPUMA, the GPU foam project, for example. But I would see them as a complementary thing, because basically they are all working into the same direction. And I would argue actually the largest competition for the OpenFOAM world is all the other GPU-capable to some extent open source and commercial tools which are out there now. And to only name some of them, which are, for example, DL2, NEC-O, NEC-RS, Pele, Moose, OpenLB, Phoenix, Dune, FluidX, 3D, and so on. And if you compare like people working on the individual projects, you will see that, for example, Moose is very active. I checked Moose yesterday, and they had like 30 active developers in the last 30 days. And DL2, for example, had like 21, NEC-O 10. And we as a community, I think we really need to come together and work in a similar direction in order to keep OpenFOAM relevant and keep OpenFOAM evolving. Yeah. And in my opinion, the only real way to compete there is we need to leverage the strengths of the OpenFOAM community, because OpenFOAM has a large community. There are a lot of institutes working with OpenFOAM, and there are a lot of institutes working on specific implementations. But we really need to bring them together, I think. And we need to attract like young people and young researchers, and therefore we have to look what are people working on. For example, a Python interface and so on. So what is OpenFOAM? What do we want to consider, or what do we want to bring forward? So currently, what we think about as NeoFOAM is basically the project, and in the project we have several tools. One is Neon, which is the computational backend, and then we also have Foam Adapter, which ties together Neon and OpenFOAM. So what made OpenFOAM strong? I would say, first of all, OpenFOAM's DSL is very powerful. So you can implement all the PDEs you are imagining and have a powerful solver for the PDEs. And around them, you have a lot of applications like IcoFoam, SimpleFoam, and so on, and a lot of libraries which provide like turbulence models, thermophysical models, and so on. So what we think needs to be re-implemented to some extent is basically only the core, which are data structures and numerical schemes, and to bring, for example, new matrix formats like besides LDU, COO, or CSR, or more advanced or more complex matrix formats. But also we need like strong APIs, because the HPC world is more modular than what it has been when OpenFOAM first started. So we think we don't want to reinvent the wheel. For example, if one wants to solve a system of linear equations, well, then we should just use one of the tools which are out there, for example, PETSI or Ginkgo or AMGX. Also, there are a lot of third-party software like Adios, Precise, Sundials, which can bring a lot of functionality to OpenFOAM, but we really have to look how to integrate this software. So currently, what our architecture basically looks like is we have Neon, which is the MIT licensed core of what we do, and that basically leverages Cocos for the platform portability aspect. And we use Sundials, for example, for time integration, and Ginkgo and PETSI for the linear solver parts. And in order to connect that to OpenFOAM, we have something which is currently called the adapter, the foam adapter, and this brings together like basically OpenFOAM and Neon. So since this is not only a project by me, I think it's really important that it becomes a community project where people can contribute to it, and which consists of different institutions who are working on different ends of the project. we already have some valuable contributions by different individuals, also different institutions like the SCC, the Scientific Computing Center at KIT, or there's some contributions by HLRS, also Upstream CFD and TU Munich. So how does it look like on a technical level? So we want to have something which is really simple to integrate. And the basic building block is the executor, and the executor is just a notion where you want to keep your data and where you want to do your computations. And if you want to offload it to the GPU, you instantiate a GPU executor. So this can also be selected at runtime. So basically, you only change your control dict and say this runs on the GPU or that runs on the CPU. And then the basic building block is what we call a field, basically. And the field just gets this executor, and you can point to the data from the OpenFOAM side, and then Neon takes care of offloading all the data to the GPU and then doing the computations. And the next step is also the expressions. So an expression is very similar to OpenFOAM's DSL. There are some minor changes we do there in order to be a bit more expressive. I think it helps if we call our namespaces, for example, implicit and explicit, to make it very clear that this is an implicit operator or another one is an explicit operator and things like that. But besides these namespaces, and can also use the namespace in order to make it a bit more concise and less verbose, the DSL is almost identical to what you have in OpenFOAM. So we already had a first release, which basically gave the principal architecture, also added a lot of like unit tests and unit testing to the picture, and we run, for example, on AWS hardware to just directly test on GPUs as well. And the first results we had were quite promising, I would say. But the first example we were able to run is just a simple advection test. So currently we are working on the next version. I hope this one works. So the next release will be quite soonish, and that also implements a lot of implicit operators and basically enables to run the whole workflow on the GPU of matrix assembly and solving on the GPU. And with that, not to spend too much time here, I would say, I really want to stress that we welcome any contributions from the community, because we think like this project really, like everyone who contributes something will profit of the contribution of others. So there's no monetary incentive for anyone. No one is making any money out of it. So we are really working on developing something strong for the community here. Everything is open source. You will find it on GitHub. We meet regularly. We have a GitHub channel where you can get like help and support. There's a regular meeting every Thursday on Jitsi. And yeah, there's also a public roadmap, what is up next for the next release. And yeah, that's basically it from my side.
Okay, thank you, Gregor, for this interesting presentation of what you are doing. Very nice. So the next speaker is Charlie. Okay, so Charlie, are you ready?
Yes, I'm ready. Hi,
oh, okay. The word is yours now.
Lovely. I'm going to just figure out how to share the correct screen. Oh yeah, that should be That should be the one. Can you see my slides?
Yes. Yep.
Excellent. Can you also see the attendance list, or is that hidden?
It's hidden.
Like the.
It's hidden. No
Okay,
worries.
that's good. That's good to know. Good to know. Okay, jolly good. Yeah, so thank you very much for the invitation to talk, and also for the efforts in this very important direction. It's a really sort of high priority topic for us, as I'll explain. Yeah, without further ado, I'll explain. Oh, I took a little bit of liberty with the title and changed it slightly. So we're talking about benchmarking GPU codes for scale resolving simulations in industry. We do a lot of work for the automotive industry, but not only. And also, we aren't the automotive industry, and the original title sort of maybe implied something that's not quite right. I hope that's no problem. So just very briefly to introduce Upstream CFD, we're experts in high-fidelity CFD simulations for aerodynamics and aeroacoustics. We're based in Berlin, and there's 10 of us at the moment, 5 co-founders. And yeah, we have a real focus on quality and reliability in the way we work. And we've been working on OpenFOAM since 2011. So, you know, not the weren't there right from the start, but we've been around for a while, and we've also made a number of contributions to the public code over the years. We see our mission, so the reason we exist, is to enable the deployment of high fidelity CFD in industrial design processes. And what that means is identifying barriers to adoption of high fidelity CFD and overcoming these. And we support industry partners to do this and to get the most out of the technology. And when we talk about high fidelity CFD, we mean scale resolving simulations. So for turbulent flows, then we're talking about the kind of simulations that you see in these animations on the right, where the turbulent eddies are resolved basically using compute power, which reduces the amount of heuristic modeling needed, and it strongly improves the accuracy, especially for massively separated flows of the kind you see here. But it also adds a considerable increase in computational cost. So since this is what we specialize in, then that computational cost is very much seen as one of the main barriers to adoption of this technology. Hence our very strong interest in overcoming that barrier. And we see GPU very much as an enabling technology for scale resolving simulation and everything that it offers. So more accurate drag prediction for cars, for example, related to emissions and range of electric vehicles, and also aeroacoustics. So the top animation is from an aeroacoustic simulation, looking at aircraft noise, simulating it so that it can be reduced. So yeah, as mentioned, this topic, GPU implementation, is of very high strategic importance for us because of our speciality in these very costly methods. So the kind of stuff we've been doing over the years, we were partners in the EU Exafoam project, also in the Exasim project, which Gregor just outlined. We've been working with industrial clients to assess GPU code capabilities, and I'll show some results of that here. And we contribute to the NEON initiative that Gregor just introduced. And also another thing that I've been doing quite a lot, especially in the last months, is really reaching out to all these various OpenFOAM GPU initiatives and encouraging everybody to exchange and talk to each other and find out to what extent they can collaborate and how the different initiatives are complementary. And that's actually been very successful. And I think today's webinar is very much in that spirit and very welcome. So I'm going to talk first about the importance of KPIs, so key performance indicators, metrics, which enable meaningful CPU versus GPU comparison and also comparison of different GPU codes. Then I'm going to do some number crunching to analyze one of the new generation of commercial codes, which has come out recently with very impressive performance. then show some of our testing of the Zeptofoam, which was a prototype for SPUMA that we did together with the colleagues on the line from Cineca. And then look towards the future, where we basically see SPUMA and NEON as two complementary initiatives, which we're very much focusing on with slightly different objectives. Yeah. So starting on the benchmarking and KPIs. So this was something which kind of, we started working on this together with colleagues at Wiki and some other partners in the Exafoam project. And yeah, it's really important also to analyze essentially the business case. Does it make sense to switch to a new GPU version, or how do these things compare? And it's quite difficult when everyone's running different test cases, and when they say a word like speed up, then they mean something different. It depends on what you're thinking about, and it's very important to have some clarity on that. So alongside the actual measures, it's also really important to have a relevant kind of simulation. So for us, that means, for example, incompressible DES, so these scale resolving simulations. The lid-driven cavity is very useful for early stage benchmarking and analysis, but the results often aren't very representative of these unsteady scale resolving kind of simulations. It's also really important to have a strong baseline that you're comparing with. So the CPU, when you say speed up versus CPU, it's really important that you're choosing your optimum setup, running at the optimal efficiency, giving basically the CPU benchline the best possible results. Otherwise, it's very easy to skew results and draw false conclusions. And then, the idea is you could say, okay, these are our 2025 CPU benchmark or baseline, and then that could be updated each year, for example. And you can say, compared to the 2026 baseline, the GPU code is now this much better, etc. So looking at the actual numbers or the quantities, I find it really helpful to start with a number that I call CPG, which is the kind of, which stands for cores per GPU. So what that means is how many when I run on one GPU card, how many CPU cores of performance does that give me? So the equivalent performance of one GPU card versus multiple CPU cores. And that's a very useful metric. It's very easy to understand. And then from that metric, you can evaluate a whole bunch of more relevant metrics. So you can look at essentially the speed up, so the time to solution reduction factor, by taking your CPG, plugging in the number of GPUs you used and the number of CPU cores you used, and that gives you the acceleration of the time to solution. Remember, we're comparing an optimum CPU setup with an optimum GPU setup. Yeah. Then you can look at the cost to solution reduction factor, and then so then you need your information on how much a CPU core hour costs and how much a GPU hour costs. Talk about that on the next slide. And then also energy to solution is done in the same way, looking at the power consumption of CPUs versus GPUs. I sort of deliberately define these numbers so that higher numbers are better in all cases. I think that's also quite helpful. So that in the following numbers you see, it's always bigger numbers are better. So the left-hand table is just for completeness. So when you can look at the slides after the webinar and really understand exactly what I'm doing. And then to talk a little bit about the approach for cost, what we like to do is to use data from cloud computing providers, because they are representative of all of the components of the cost. So the purchase cost, the energy cost, the cost of running. And then what we do there is we look at the sort of lowest prices available on AWS, which are publicly available for the case of a 3-year bulk buy discount. So that takes out sort of market fluctuations as much as possible. And it also gives you very relevant numbers. So those numbers can be used as a surrogate number, just an indication if you're using something else, but for us, it's very relevant because we run in the cloud, and this is the real, the costs that we really pay. For energy, it's obviously a lot more debatable. The approach that I've taken is to use the thermal design power of the chips, if available. It's not always information that's available. And then just to assume that cooling energy would sort of scale proportionally to that. But yeah, no doubt HPC experts with access to the real energy consumption of their systems would probably prefer to use more accurate numbers. So yeah, now to look at the competition first and to really sort of give the motivation. This is some analysis of results from the 4th Automotive CFD Prediction Workshop, which we were involved in co-organizing last year. And there it was common test cases, automotive CFD cases, and lots of different participants using different codes. And alongside concentrating on the quality of the results, there was also a lot of focus on the HPC performance in a dedicated HPC focus group. And yeah, participants gave very detailed information on the compute performance. And this was analyzed by Herbert Owen from Barcelona Supercomputing Center. And he showed a number of charts with different kind of cost metrics. This is an example, dollar cost per time step and cell. He also looked at other metrics. And I think the first thing that jumps out is you have to see that this is a logarithmic plot with, okay, the top, oh no, there is a point there. So we've got almost 1, 2, 3, 4, 5 decades of difference between the various codes. And then what he pointed out is that there were only 2 CPU results below that line. So it became very clear from that workshop and all the participants that GPU is a real game changer and makes whole things possible. What you do have to bear in mind though is that there were all sorts of different codes, so it's not all due to GPU. Like a lot of this is because some of the codes were lattice Boltzmann versus finite volume, or some of them had Cartesian grids instead of body fitted grids, or implicit versus explicit time integration. So when choosing a code to benchmark the potential performance that we could expect for OpenFOAM, I chose a code that was A, among the most highest performing codes, but B, also with a very comparable methodology. So also a second order finite volume code, running DES on body fitted meshes with double precision. Yeah. So I'm going to speed up a little bit. The analysis basically of comparing OpenFOAM and the reference GPU code, making corrections for the grid size, gave these numbers. So the GPU code was unlocking about 680 cores of worth of performance per GPU. These are on A100 GPUs, not the newest anymore, leading to time to solution reduction of factor 18 and cost and energy solution reductions of about a factor 6. Estimated. So those are real eye-popping numbers that really get people's attention, and certainly got our attention. And this is what OpenFOAM needs to match, and it needs to do so fairly quickly. So can I just ask how much time I've got? Just a couple of minutes now, isn't it? About 2 minutes.
You're supposed to end now.
All right. I will.
Yeah, but you have you can have another 2-3 minutes. Yeah.
I'm sorry. So this is I will just show the results of the collaborative work we did with Chineka to evaluate Zeptofoam, which was a prototype for SPUMA. And we ran this test case, which is an automotive generic type of test case. And these were the numbers that came out when we compared the most efficient setups. We got a CPG of about 140. It turned out that the GPU solution was actually nearly a factor 2 slower, but we had positive results on the cost and the energy. So we had reductions of cost and the energy to solution. So very different numbers to the reference commercial code, as you see. Yeah, this CPG of about 140 leading to these numbers where we're not achieving a benefit on all three metrics. And then when we look ahead to SPUMA, the white paper that was published indicates a CPG, so they've implemented some further improvements, that the CPG is going up to 250, and that would give us about equivalent speed and much greater cost and energy reductions, so getting between a factor 2 and 3 of cost and energy reduction, if those numbers would apply to the same test case, which we hope to test soon. So I have, I think it's just one more slide. Yeah, the analysis of the new generation of commercial codes shows enormous potential. And for OpenFOAM, this really means the pressure is on. Users of OpenFOAM are taking note and are getting increasingly impatient to be able to do the same. It's very important when you're benchmarking to have a relevant case and also a strong CPU baseline. And I'd like to just point people in the direction of an initiative going on at the OpenFOAM workshop, the OpenFOAM HPC Challenge, which is also using a common test case centered on OpenFOAM. So that's going to be very useful. We see SPUMA as a very important step forward. So we expect from our analysis significant reductions in HPC cost and energy consumption, and that the simulation speed will be competitive with the most efficient CPU setups. So that's the way, you know, we need to do the actual testing, but from the sort of preliminary analysis, that's the way things are looking for our kind of application. Yeah, newer GPU architectures and future GPU architectures will increase these benefits further, of course, because the growth in GPUs is quite faster than it is for CPUs. But of course, the same is going to be true for the competing codes. They're also going to get, you know, the delta will also grow. So yeah, in a nutshell, we are focusing on these two complementary initiatives that have different priorities. So we see SPUMA, it is, and the other one is Neon that Gregor introduced. So both are implementations where the whole simulation runs on the GPU. SPUMA is essentially the same code, which has been ported to GPU via a minimal invasive approach, and that has certain very clear advantages. Whereas Neon is a completely new CFD backend that is being optimized from the ground up for GPU. So with SPUMA, we expect a moderate but significant performance boost. Whereas for Neon, the target is maximum performance boost. SPUMA is available today, and Neon is still a work in progress. So yeah, that's the end of my talk. Thank you very much. Sorry for overrunning. Looking forward to the discussions later.
Don't worry. So let's move on with the next topic regarding the coherent mesh provided by Gregor Weiss.
Yes, good morning. Good morning, Shimon. Good morning, Ettore. Thank you again for inviting. Let me try to share the screen. And now it should be in full presentation mode. Shift this over here. Okay. Yes, so I am part of HLIS, the High Performance Computing Center in Stuttgart. And as you have heard before, we were also partner in the ExaFoam project. And what I will present today is essentially what was finished last year already in 2024 with the ExaFoam project, but very much appreciated by this GPU topic now. Because of, like what Tommaso said earlier, coherent or contiguous data accesses are very important for GPU. So let's just dive in. So first of all, let's have a look at what kind of problems we encounter when we use I/O or parallel I/O in OpenFOAM. Essentially, the legacy I/O is not parallel in a sense of where you would put parallel I/O, that it somehow communicates, orchestrates its I/O via maybe a subset of ranks. Instead, every rank writes, and that's why you have really the number of files, no processor folders that will be generated by each rank, and then you have these number of processor folders scaling with the larger you go on supercomputers. Once you decompose your case, you're very much fixed. That was also mentioned by Ettore earlier. Other benefits post-processing were appreciated earlier. When you decompose the case, you have to reconstruct it, and this reconstruction also takes time. And mixing the simulator with output fields is actually what you will have to deal with as a user, because your field data is in the same as, let's say, your boundary settings that you have for your pressure or velocity file data. You have a minor problem is that you have also duplication of data on your boundary, on your processor boundaries, and then the current fix, let's say, to the scaling files and hitting the quota on supercomputers is the collated format. But it only solves half of the problem, because the mesh representation is still as distributed or as fragmented as I will show later on. And the only fix that we did essentially is here shown on the right-hand side. Before you had the connectivity between faces, points, and cells, so your mesh entities. It was a face-to-cell connectivity or adjacency, and we basically flipped this arrow downwards. So you have now a coherent connectivity from cells to faces to points. More about GPUs is what we recently also, as in the Accelerat project, where we helped the Neofoam project. With the foam adapter, as Gregor said, this is basically where you run your cases. This is the API you would run when you want to run a case using Neon. That combines open foam functionality and whatever is currently work in progress in Neon. For the sake of GPU porting, the I/O is still landed fully by the open foam I/O. But this has a big drawdown on the I/O performance, actually. So we see that we measured that when we have to load the mesh, this takes 10 minutes to load 128 million cells, and these are really the case sizes that you will use for GPU computing, because GPUs have this bigger processing power. It will definitely increase these demands on I/O, or in very general terms, these gaps in the memory hierarchy, such as I/O, they certainly grow. Yeah. So let's have a look at our fix, this new data structure for unstructured polyhedral meshes, which is also, you could say, it's somewhat general to polyhedral meshes. First of all, again, open foam, when you decompose your case looks like this. You have your processor folders where each processor has a part of the mesh, and the original mesh now is actually fragmented onto these processor ranks. So entities will be irregularly associated to new parts of meshes, renumbered from 0, and everything or the data access pattern becomes very fragmented and irregular in that sense. And again, the number of files, as mentioned earlier, now scales with your parallelism. So the user experience, all in all, is very complex and time intensive. the fix is, of course, to make it contiguous. So to come up with something that you could basically slice or chunk your original mesh onto different processors. And the basic 3 rules that we applied were sorting rules. So first thing, to sort faces and points by the occurrences in the cells. And let me emphasize the point on sorting. So this is really just a sorting process or a sorting algorithm. We will have the cost of sorting essentially in the end. And then because it's now sorted, the ownership, let's say, or the connectivity from cells to faces can be flipped around. And this is this downward connectivity. Now you have a tree where you start with your cell indexed lists at the top, and those implicitly, they can read a chunk from face ordered lists. So this ownership is now implicitly incorporated, and then you go to point ordered lists. You immediately can use slices of those. So again, it's a coherence in between your dimensionality layers, 3D to 2D and 0D in OpenFOAM, and then you have this sliceability across processors. So you have a parallel tree data structure that ends up with a contiguous data access pattern. The second part of it is fixing parallel I/O with ADIOS 2. So that is what we used. We used ADIOS 2 as a parallel I/O library. And before doing so, we also scaled it and looked at benchmarks, testing ADIOS 2 and also MPI/I/O, other approaches. And we found that ADIOS 2 was the best one performing out of the box, let's say. So with MPI/I/O, for instance, you will always write into one file. That is something you can manually configure and tune, and you will also achieve similar performances as ADIOS 2. But out of the box, ADIOS 2 gives you, for instance, a flexibility of the number of files, and that's why it can also scale up to 32 ranks, as we did on the Hawk supercomputers, which amounts to 4,000, more than 4,000 nodes. This was the past CPU machine at HLIS, which is dismantled now and actually in favor of a GPU machine. So there's really a big need for GPU codes coming. Other features from ADIOS 2 that brought us in were string identifiers to organize the database, span containers, which is a very low-level feature, let's say, asynchronous writing, contiguous access pattern, but also compression, which you can use on the fly. So the combination of those two things, reorganizing your mesh, creating a contiguous data access pattern, plus a really performant parallel I/O library, gave us the gains in the end. So again, the user experience was so cost and time ineffective. Now it becomes so much more effective just because of the sake of not having to use processor folders anymore. Whether you run serial or parallel, you will just have your time folders as you're used to in OpenFOAM. So this was an enabling technology on PETA and will be on exascale computing machines, just for the sake of inodes and quota limits on the parallel file systems, but also for the case preparation, the pre-processing, your decomposition and meshing, so block mesh, decompose par, now is really accelerated because of the aforementioned sorting feature in the coherent mesh. So this sorting algorithm only needs a n log n time complexity, as you can see over here, but for the collated format you have a n squared time complexity because it has nested loops. And there you hit quickly essentially the wall of your queue systems to pre-process your case within 24 hours. And now you can, with the coherent format, you can anticipate these speed ups of 10 to the 2, 10 to the 3 for your billion grid cell cases, really GPU relevant cases. In the end of the Exaphone project, this was also reason for this record run on the FastHawk supercomputer at HLIS on these 4,000 nodes. Again, emphasizing the user experience just a bit more. It reduces the number of files, as I pointed out. These processor folder files are totally gone. You really just have your field data, the binary field data within these adios files. And then we still separated pressure or flux or velocity metadata where you describe your boundary condition into these ASCII readable files, so you can quickly open, edit things, so the user experience becomes so much easier. You can essentially restart on any number of processors, then the mesh will be chunked regarding to these number of processors. You don't need reconstruction because the processor folders are gone. So this tool, the reconstruct part tool, is essentially gone totally. And in some, you minimize the chain in pre and post processing steps and tools. With that, I can conclude. I hope I'm still within the time somewhat.
Yeah, don't worry.
Very good, because yeah, very much looking forward to the next talk. Actually, myself, Shimona. Yeah, here we can just make this point-to-point response essentially. So this legacy format not being parallel, now the coherent format really is a parallel I/O for OpenFOAM. It reduces the number of files because we use adios too in the backend. We have a flexibility even in the number of files or in the number of ranks, which gets rid of this problem that we have a fixed number of processors in the legacy I/O formats. Reconstruction is totally redundant. We have separated field data and metadata. No data duplication is required anymore, and especially this n-log-n time complexity gives us a lot of gain on the pre-processing. Nevertheless, for GPU, I believe very much, and I think Ettore, as you and Tommaso, as you pointed out, it's very much required to have a parallel I/O with GPU. Who is drawing on my slides? Anyhow, for GPU, you have these high processing capabilities, so parallel I/O is much more important. And in the end, I can actually recommend for anyone using a ESI version, a Keysight version 2406 or 2412, there's a current branch living out there. So rebasing things like SPUMA or using these versions on the NeoFoam side would be already capable of using this new I/O, coherent I/O. So thank you for your attention. Thank you again for inviting. And this acknowledgement also goes out to my colleagues and collaborators from the Exaphone project. Thank you.
Thank you, Gregor.
Stop sharing.
Okay. So the next presentation is mine. Okay, so I'm going to present SPUMA. Let me show the presentation. Okay. Now let me share the screen before. Okay. Can you see my screen? Okay. In presentation mode. Okay. Okay. I'm very happy that after 1 hour we still have more than 90 persons. Okay. So let's start with the presentation of SPUMA, our GPU porting of OpenFOAM. And this is the outline of the presentation that recap the basic features of our development. we already talked about what SPUMA is, which is a minimal, non-invasive GPU porting of OpenFOAM. Minimal non-invasive means that all the algorithms, all the metrics data structures, everything is the same as OpenFOAM. So finite volume, segregated, LDU, CO format, everything remains the same. It is portable across different hardware. At the moment, we run on NVIDIA and AMD GPUs, but in theory, it's possible also to run on Intel, but we still haven't tested so far. It is single source code. Yes, SPUMA is a fork of OpenFOAM, so we have, due to the trademark policy of ESI, we changed the name to SPUMA, but we still have a single repository to run on GPU and CPU. We don't rely on any third-party frameworks for the porting of the code. So we still use the same philosophy, OpenFOAM, to basically provide API in foam style. It allows the developer to gradual porting new features to GPU, because here, Cineca, we are a small team, so we cannot afford the porting of all the possible algorithms OpenFOAM to GPU. So we try to find a way to allow other people, other developers, to port to GPU new feature that we still have not ported. And probably this is the main goal of this work, is to be a performance reference on accelerator without major code refactoring. So take code designed 30 years ago and see what happens on the current hardware. So this is it's a performance reference in particular for Neon. So for the next GPU code, we have a talk after mine provided by Henrik about how a new CFD code has to be, but the aim of SPUMA is to be a performance reference for future CFD codes. So when you try to port to GPU in parallel a serial code based like OpenFOAM, which is designed in more than 30 years ago, is to face these major issues related to memory management, the fact that you need to parallelize algorithm that has been designed for CPU and not for GPU. So to parallelize algorithms for a SINT, single instruction, multiple thread architecture, the fact that there is no, at the moment, a standard framework to port C++ code to GPU. So there are several strategies, several frameworks. Part of them are proprietary, but there is not a single one method, okay? So we need to face all of these issues, and we, at the beginning, try to bring new ideas into Zeptophone to see if they works, and the good ideas have been moved to SPUMA after the end of the Hexaphone project. And the basic ideas are reported below. The first one, probably the most important one, is the memory pool, which is an object where you can add and remove objects with a little overhead, ideally with constant time, okay? Then you have the executors, which is divided in a backend and a front end. Okay, the front end is basically the API that developers can use to port algorithms to GPUs, and the backend is where the proprietary code is wrapped, is hidden. Then there is the transparent use of unified shared memory, okay, which is a feature of modern GPU that we are going to talk a little bit in the next slide, and the fact that it's possible to use a linear solver provided by third-party packages using the runtime selection table. And this is normally, it requires matrix conversion. So SPUMA relies on the modern feature of current heterogeneous computing platforms. As I tell you before, we rely on the unified shell memory, and unified shell memory is used only for the data access, or the data structure that has to be accessed on the GPUs. For example, the mesh. Okay, the mesh is read from the disk. Okay, is basically computed, pre-processed on the CPU side, and at some moment, in some part of the algorithms, data are moved to GPU transparently without the manual, without any kind of development from us. And this kind of feature allows developers for a gradual porting without breaking the code. So you can increase the number of features that you can port to GPUs without breaking the code. At the beginning, you probably have performance issues because you have memo copy between CPU and the GPUs, but it's up to developer to work on them and try to remove it the most as possible. The other point is to leverage on the C++ feature of modern compilers that are supported by most of the GPU vendors. As I told you before, we want deliver executors where the front end is written in C++, like stdpar of the C++ language. Okay, so you still write in C++, but only the low-level part is written in proprietary code like CUDA or, for example, heap for AMD. But these parts are small and confined in few files, so they are easy to be maintained. This is another important topic, in my opinion, which is the computational load for CPU and the computational load for GPU. Probably all of you know that the best performances on CPU are achieved if you have less than 20K cells per core, okay? Which means in modern CPU to have the linear system, so matrix, right-hand side, and vectors, that fits into the L3 cache, which provides huge velocity and a super linear behavior. This is the best performances you can achieve now with CPUs. On GPU, the situation is different because GPU needs to be oversubscribed in order to get performances, and you need to have at least, running SPUMA, at least 10 millions, probably better is 12 or 15 cells per GPU. So there is 3 orders of magnitude of differences between CPU and GPU. So it means that for our large industrial problems, few GPU are necessary. Okay, for example, 100 million cells requires, say, less than 10 GPUs. If you have a very big mesh, it's difficult to satisfy the constraint of CPUs, just to have the linear system in L3 cache, if you have not a huge number of cores. So if you can access to a tier 0 machine like the Leonardo data center, it's probably possible, but it's not always the case for SMEs, where normally the resources, internal resources are not so huge. In this first release of SPUMA, we ported to GPU only the incompressible solvers, so basically Pimple and Simple form. Okay, and we decided to deliver performance metrics for the 3-wire industrial test case. Okay, so there are several meshes you find on the web. There is the fastback geometry that you find in the org repository. And there is another configuration, which is called Open Clue School Inversion, that you find in HPC Technical MIT repository. For the last one, a very huge mesh of 236 millions have been provided by the HPC Technical MIT, in particular by Wasserman. And this is the same mesh that going to be used for the next workshop in Vienna. Okay, this is the slide where I report the speed up. No, this is the metrics that has already been explained before by Charlie. It's called, he has a different name, but this is the a metric that reports the equivalence, no, between CPU and GPU. Okay, these numbers have been obtained running the open cooling geometry with 235 million cells. Okay, and the reference is the run using 200 cores. So basically 2 nodes of Leonardo data centric. And we perform, you see, 7 more runs from 200 to 1,600 cores, and from 8 GPUs to 24 GPUs. For this particular case, we use AMGX, so the multi-grid solver provided by NVIDIA for the pressure solver. So the metrics, okay, that is reported here in formula using the speed up of this plot, okay, reports a value of equivalence between CPU and GPU of 220. Yeah, this number is normally in the range of 200 and 300, depends on which kind of reference you're using, but normally this is the range. 1 GPU equivalent to 220 cores, it doesn't mean that I run the case with 1 core and with 1 GPU. Okay, you see, this matrix has been performed using, by comparing 24 GPU with respect to 1,600 cores, which give you this equivalence of 220 cores with respect to 1 GPU. Yeah, then we can talk about scalability. So what happens if on strong and weak scaling using the same geometry, okay? And what we see, for example, this is Leonardo cluster. That in the next slide we will see what happens on Lumi using AMD GPUs. Let's concentrate now on the moment on strong scaling. You see that OpenFOAM using the native multi-grid solver GMG scales almost linearly. There is a superlinear behavior between 200 and 400 cores, and then starts to bend. Okay. Regarding SPUMA, we see that GMG scales worse than AMGX, and we will see in the next slides that GMG, as it is, so using the data structure and the algorithms of GMG, doesn't scale very well. It scales very bad. So it requires, this is so that it requires, in our opinion, major factoring in order to have a scalable solver. MGX works fine, okay. Also the weak scalability is better than what OpenFOAM Vanilla is doing. So weak scalability in GX is very good. It's good for strong scalability. Regarding the Vanilla, we see that you have this little bit superlinear behavior, but the weak scalability is not complete. Like it's not excellent. On Lumi, the situation is a little bit different. We see a superlinear behavior in the range 200 and 800 cores for OpenFOAM Vanilla. Regarding the SPUMA GMG, the scalability is the same as Leonardo. Here we don't have the scalability using AMGX because AMGX works only for NVIDIA GPU, so we don't have at the moment a counterpart proprietary code for running on AMD. Regarding weak scalability, the weak scalability of SPUMA GMG is a little bit better than what we achieve on Leonardo, while the weak scalability of OpenFOAM Vanilla is much more better than what we see on Leonardo cluster. let's concentrate on what happens on the GMG solver. Okay, GMG, which is the native multigrid in OpenFOAM, which is represented with the orange line, using few GPUs is much, much faster than NGX. And this can be explained by the fact that GMG has geometric information taken from the mesh because it's built upon the data structure of OpenFOAM, can agglomerate the hierarchies. So you have a sort of overhead at the beginning of the simulation, but then you can exploit the caching of the hierarchies, even if the matrix changes from one step to the other in the simple algorithms. This cannot happen with AMGX, which is purely algebraic, so it cannot cache the hierarchy since the coefficients of the matrix changes. Okay, one solution is to rely on a different, for example, algorithm that has the pressure solver with constant coefficients, but this is another topic. But what happens if we increase the GPUs? That AMGX scales, say, well, so scale good, but GMG basically it doesn't scale, or on 8 GPUs is even slower than 2 GPUs. So we only have a small amount of performance improvement. You move to 4 GPUs, but then performance starts to increase a lot. Also, weak scalability. You see, GMGX is very good with scalability, but GMG has a very worse with scalability. And this multigrid is relying on a very basic smoother like the Richardson, which is sort of diagonal based, okay, which is a parallel smoother, but it means that this worse scalability is not related to the smoother, but for sure on the construction of the hierarchies of the grids. Okay. As I told you before, SPUMA is a minimal, non-invasive porting, and we use the same matrix format as OpenFOAM uses. The matrix format of OpenFOAM rely on exploit the characteristics of the finite volume matrices to have a symmetric sparsity pattern. But the main problem, which is nice, for memory-bounded problems, okay. But the main issue here is that the fact the matrices, if you're using hexadominant meshes, is that you have very low number of non-zero per row, which does not allow an effective vectorization. So this is an issue for sure for CPUs, but it is a more issue on GPUs. So it's hard to improve performances using this kind of matrices provided by finite volume. Doesn't mean that you cannot have a gain, but it's hard to have it. This is the reason why GPU porting and with new matrix data structure was not the priority in this work. Another important topic is that how much time is spent in the assembly and how much time spent in the solver part. Because the solver part, if we don't change the numerical algorithms, are not affected by a major refactoring of OpenFOAM, because SPUMA uses Jinko or uses AMGX, whatever. It's the same linear algebra can be used by other codes that have a huge major refactoring, but the performances for the linear solver remains the same. Okay, so the impact is only on the assembly part, and this pie chart, okay, reflects the timings for the DRIVAR 236 millions. Okay, you see that the assembly for pressure and momentum is about 21%. Then you need to also to include the assembly of the turbulence equation, so we can estimate time spent in assembly less than 40%. Okay, so this is that only on that part you can improve the performances if you don't change segregation, simple, and so on. So my opinion, this is a personal opinion, a major effector in OpenFOAM has to reflect not only data structure, matrix format, but also the numerical algorithms. So we still want to rely on segregated, we still want to rely on array of structure of array, like we have OpenFOAM. This is, in my opinion, a very major question that we have to answer in the major refactoring. Okay, we are ready to conclude. So the last slide is related to mixed precision. Now, mixed precision is a feature that has been available in OpenFOAM from version 1906. It's basically a compilation flag. And if you activate it, okay, you have the assembly phase that run on in single precision and the linear algebra in double precision. We activate also this flag in SPUMA, and we see basically the same number that are reported in the webpage of ESI. So we found a sort of 30% less memory usage, and in average, a performance improvement of 20%. This so we found, for example, on 4 GPUs are 30% of performance improvement that starts to decreases, and on 24 we have 14 performance improvement. The reason is due to the fact that for these numbers, the GMG has been used, not the NGX, and GMG, as I said before, is scales very bad. So the impact on improvement of the assembly phase is less important when we move to a higher number of GPUs. Okay, conclusions. So now we have a GPU porting of OpenFOAM freely available via Git on an internal repository that can run on NVIDIA and AMD architecture. We have a speed up at the moment in a range of 200 and 300 for external dynamic incompressible problems, steady state, okay? On Leonardo, we see a better scalability than on Lumi. Sorry, on Lumi we see a better scalability with respect to Leonardo, but a lower speed up due to the fact that AMD CPUs are faster than Intel ones. So the speed up is a little bit less when comparing AMD GPUs with AMD CPUs. And mixed precision can improve performances, but no more than 20%. So yeah, advantage, but not so huge. Okay. Due to the time constraint, I forgot to add a slide related to the energy. Okay. We have also numbers related to energy consumptions on the paper, and we see that we compare basically one node of Leonardo, so using basically 4 GPUs, and how many cores? I don't remember the name. Or the same simulation, and we see that we have a reduction in terms of energy about say 3 times, 3 times of reduction. So last slide is related to future perspectives. Basically the development roadmap that we have here in Cineca. So 3 steps are related to linear algebra. Basically improvement of GMG because scalability is very, very bad. The possibility to interface towards Hyper, which can offer also solutions that runs on AMD and not only on NVIDIA, and is not proprietary code, but provided by the Lawrence Livermore, and also works on GMG, not only on the scalability side, but also on to include new effective smooters. So now at the moment we have Richardson and the 2-stage Gauss-Seidel. So we are planning to include other ones like Chebyshev or approximated inverse. Couple solver. So we have a project where we want to port incompressible couple solver on GPU for simple form. And the last two ones are AMI and thermophysical properties on GPU for delivering a turbo machinery and air acoustics application. The air acoustics are based on CAFOAM, which is an open source application delivered by Valerio D'Alessandro. And the turbo machinery is a work that we are doing here, mainly driven lead by Ettore Fadiga. Okay, I completed my presentation. I'm on time. Probably no. So I left my word to the next speaker, the last one of this morning, which is Henrik. Let me stop.
I'm alive.
You're alive? Okay. Let me stop sharing.
Cannot start. Okay, here we go. Try again. Aha, here we go. Does it switch?
Yes.
Perfect.
Yeah.
So thank you very much for having me. I'm Henrik Rusche of Wiki GmbH from Wernigerode. We also participated in the Exafoam project and two Inno4Scale innovation studies that have happened recently. So we are quite heavily engaged in HPC recently. The history of the company in Germany dates back to 2008, and myself, I've been involved in foam since 1998, where it was still foam and not open foam at Imperial College. So let me start with our legacy. The open foam's design paradigm in a nutshell, really. So the idea of open foam was to use operator overloading to implement the CFD code. So that was Henry Weller's vision at the time. And I should note, in complementing Gregor's timeline, is that Henry started open foam even before the standard. C++ 98, that is. And it also predates the STL. So, and you can tell, and so that's why many people say, okay, why doesn't it use the STL? Well, there was no STL. So the idea was, can we implement a CFD code in C++? And at the time, Fortran 77 was the standard. So it was a drastic change at the time. So we used object orientation to implement the physical models and C++ to implement the algorithms, but using a extension to represent partial differential equations. So normally what I say is open foam is a kind of MATLAB for partial differential equations. That enabled the user to implement turbulence and combustion models in a day. Testing takes still a lot longer. And the paradigm of implementing open foam was that all the work is in the linear solvers. And as we've seen previously, that is not actually the case anymore. We also said the file system is a good parallel database, which is something which led to the ideas of the coherent file format in the Exafoam project. So I consider that one at least conceptually fixed. Open foam was always industry focused. because it came from Imperial College, and the links that we had to commercial CFD at the time, and it was really a keep it simple and stupid design. So that's OpenFOAM in a nutshell. So if you think about next generation CFD, it's also a question of where do we stand with CFD today, and where do we come from? So we had this drift from in last century, from in the 2000s, 20 years ago, where we replaced many of the Fortran applications with C++. And I guess a lot of the older people remember the discussions. Yeah, you cannot write CFD in C++. It's never going to work. It's too slow. And to a large extent, I think we proved them wrong. However, we also inherited a few issues related to memory, which we could fix. And that enabled us to tackle many more real-life problems, and partially because it is much easier to develop in C++ than in Fortran. And using a DSL like OpenFOAM rather than coding things in a functional manner. So I think the legacy of OpenFOAM is actually its DSL, and the way that we think about CFD in terms of partial differential equations, operators, matrices, and how this could fit together and be made visible in the code. At the time, there was a lot of discussions about lattice Boltzmann, and my observation is they haven't taken over the world as promised. That's an observation without actually knowing enough of those codes. There is also a lot of work in spectral elements, discontinuous Galerkin, and they seem to be on the rise. And is that only in research? I'm not sure. And commercial CFD, my observation is it's still dominated by finite volume. And I think that will remain to be the case for the foreseeable future. So what do we need to tackle? We need to tackle optimization, multi-scale, artificial intelligence, the new hardware, as has been reported in quite a few of the preceding presentations. We need to be able to find sensitivities of complete models, but without the pain that it inflicts today. We need to embed and interface much more easily. Hardware trends bring us back to the 90s, and I have a slide for that later. Okay, I guess you all know that the hardware trends are working against us. Memory becomes slower relative to the CPUs and the compute. And I should also add an insight that I had visiting in Barcelona. And it is from Hartwig Ans, and he mentioned that the design of the GPUs is not driven by HPC. It is driven by data science and artificial intelligence. And that means there will be devices that are fast for low precision, not for high precision. And there is a couple of factors, and they are working against us rather than for us. For me, this is the hardware trends of today. They are sort of going back to the past and projecting them into the future. So if you look on the left-hand side, it's a time plot of the top 500 machines split up by hardware. So at the time when OpenFOAM was written, there was a sizable amount of vector machines, and actually the decision in OpenFOAM was not to support them too well. and RISC was coming up, and that also went, the transition into x86 was quite smooth. But you can see that those large Linux clusters are on the way out, and we will see accelerated partitions. So what is everybody else doing? So I think the world is a bit larger than finite volume, so maybe it makes sense to have a look. And I can see probably 3 different designs in finite element and spectral element code design, and that is, one is to use Python to generate fast optimized code and compile it before starting the actual calculation. So that's something that you would find in Phoenix or Firedrake. And this is something that you find in a lot of finite element codes, because the choice of the element, you don't want to have all these elements hard-coded for all the ansatz functions and partial differential equations. So they have a bit more of the problems, and that we probably have as well, but they solve them, for example, by using a preprocessor step, or today, like in NEC-RS, you use just-in-time compilation. They use Oka, or you implement a custom abstraction layer so that you can run different hardware, like in NECO. Interestingly, the last 2 are descendants of NEC 5000, and they can't agree on how to proceed. Obviously, all of these design choices have pros and cons, and I guess the dust hasn't settled what you should do. I haven't mentioned Cocos, but obviously it's another contender. I guess that dust will never settle. It's a continuous quest, and but anyway, there is a lot to learn from these codes. Why do they use it, and what does it give them? Okay, so what is the future of our legacy FE applications? Do we throw them away, or what is the plan for them? So my observation is that a lot of these finite volume-based applications from the 2000s, they lack a good support for GPUs. That's a problem, because upcoming procurements of hardware will be GPU only. And that is the case, for example, at HLRS, which is actually, normally it's leading an industry-based compute center. And, but they move away from CPU only. So running large simulations will be increasingly expensive. And on the other hand, there is these finite-based applications, and they are the workhorses for many industrially relevant applications, and they constitute a substantial investment. And I think that is worth saving. We should note that the computational backends, so matrix assembly, solvers, the stuff that the user, even in OpenFOAM, rarely sees, is maybe 5 to 10% of the applications. And I had a discussion with Sergey this morning where he said, okay, well, is that in code, lines of code, or what is the metric for the 5 or 10%? And I said, well, I don't know. I counted the lines, but if you think of development time, I would say it is even less. The development time of those backends is less, because substantial amount of time went into making OpenFOAM feature-rich. And the backend hasn't received the same attention, primarily because there wasn't a need for the last 10 of the 20 years that it's alive. I think that is, to some extent, that's true also for a lot of the other FE applications that are around. So it is worth looking at what could be achieved when we make the code, rewrite the code, and what are the specs and what would we like to support. And I made a long list. I will quickly go through it. And then one is the mesh type. So I think there is a benefit of having just boxes, or have specialize on the mesh type locally, because as Simone said, we have a problem with computational intensity, and the less memory we read, the better. And having no addressing for parts of the mesh is probably the best. There's also things about matrix format. Should we use COO and should we use CSR with or without fill-in? I think the answer is we don't know. We can also go back to the nice question of mesh traversal, phase-based, cell-based. Again, I don't know. And discretization schemes, flux. I would like to use flux functions for part of the systems, so that would get me into the turbomachinery business and the density-based solvers. And I need to be able to specialize on the hardware, vectorization, and GPUs. And by the way, vectorization becomes possible if parts of the mesh are regular. So then there is no indirection, and vectorization will come naturally. Furthermore, we need to specialize on memory specifics, as we've seen with the unified memory. But honestly, I have no idea what will happen next day. So we also need to specialize on the precision, and that goes with the earlier comment that I made on what is the GPU hardware and the precision, and it basically about how to support, for example, tensor cores and make use of those. That's today, but tomorrow I have no idea what the hardware will really look like. And ideally, if we want to select the kernels at runtime, doing some runs, and some of the codes that I mentioned before do that today. Okay, so what is the next design goal for the next generation backend? I would also like to have my governing equations back. I would like to express them in a domain-specific language, just as we have this in open form today. So I don't want to lose this. And actually, this being able to express partial differential equations is one of the problematic things in open form that will hinder us to do optimization if we leave it compiled like it is today. So I would like the DSL to allow me to express any type of finite volume-based algorithm, be it segregated, that would be open form today, coupled like in form extend, or semi-coupled like in form extend. So some of the systems you take them out, transient, steady state, whatever. So I want to be flexible in formulating the algorithms a little bit like in open form today, but in a DSL, in a domain-specific language. I should also look at matrix free, because if you think about the codes that I mentioned before, they stress that to be efficient, they need to run it matrix free, and that is finite element, spectral elements. So I wonder whether that isn't a route that we should go with our codes. Certainly for transient simulations. We need to support various complexities in the mesh, multiple meshes, conjugate solutions, overset, immerse boundary, and so on. So Mind you, the specification of that domain-specific language, it can be versioned. It needs to be extendable, but the language doesn't have to be full. We just need to think about how we can extend it. And not all of the features of the DSL have to be implemented by the backend. Now, what is the benefit? The benefit is that domain-specific language gives you possibility of doing mathematical analysis, and that you need for the gradients and sensitivities and the new features that you want to support in future. A domain-specific language allows you to perform high-level optimization, so you can avoid communication where it's not needed. For example, boundary information from a gradient that is not needed anywhere in your algorithm, you can now know at runtime. We don't know at compile time today. So that's why we can't optimize for that. The DSL should perform low-level optimization, fuse loops, and again, that is needed to increase computational intensity. So how do we bring that together, and why did I mention all the other legacy codes? Well, if we take a finite volume DSL and make the legacy application, such as OpenFOAM or other legacy CFD codes, and make them to generate the finite volume DSL, give it to a compiler, compile the machine code, and then jump into it and execute it, we can plug, we can retrofit the backend into various codes. And that makes the effort much more worthwhile. So we can also adjust the backend to the host application's needs. Like, I cannot do this, this needs to be done by the host application, like thermodynamics or things like that. So you stop whatever is generated by the finite volume DSL. You stop and you hand over to the host application. And because everything is done at runtime, compiled at runtime, you have that flexibility.
Sorry, Enrique, one, 2 minutes more, no more.
Yeah, it's the last slide. So
okay, thank you.
All of the finite-based legacy applications, they have similar challenges with hardware and software design. And these challenges are interlinked, and they need to be addressed in one go to make the effort worthwhile. It makes sense to join forces between different CFD applications, and they could use the same backend. A common DSL would synchronize the language that we talk, a bit like OpenFOAM did for the OpenFOAM community, but this could span wider through different finite volume community. So we should actually aim for a next generation backend rather than a next generation CFD application or porting OpenFOAM. We should port OpenFOAM to new hardware or bring it to the next level by plugging in a new backend that can be reused. So with this, thank you very much for listening. And I don't know what the plan is, because we made it on time without the 30 minutes.
No problem.
Okay, thank you very much, Eric. I will take over with the Q&A since I monitored the chat.